this is the lesson where everything that we've learned previously, reaction types, balancing, and assigning states, all comes together. In order to be successful in predicting the products of a chemical reaction, you must be able to determine what type of reaction you are looking at based on those 5 reaction types. Remember, composition, decomposition, single replacement, double replacement, and combustion. You must be able to know what kind of reaction you're looking at and then know what pattern that follows, and also have some knowledge about states. We'll be assigning states, okay, balancing, and also, writing formulas for compounds. So, what's going to happen is I'm going to go through many examples, 8 examples here. I'll give you all sorts of tips and tricks and things that you are expected to know in this course, and I'll bring those up as we go through these examples. Have you ever seen a chemical reaction written either on a quiz or an assignment that you've been given, or maybe on a video that you've watched or anything like that? By this time in the unit, you've had an opportunity to see many chemical reactions. And then, do you ever wonder, okay, how do you know what's made? How do you know what products are made? Maybe some of you have already discovered those patterns and how they work, and we're just going to finesse things for you here. Maybe some of you are just like, nope, I have not even noticed that at all. That's okay. We'll get you there. So now that's going to be your job. Your job is going to be able to say, oh, here's what's made in this various type of reaction. I know because I know what type of reaction it is. I know how to write the formula for compounds, so on and so forth. Our first example, magnesium plus sulfur. The first thing you need to do when you come across a reaction that you need to predict the products for is determine, okay, well, what kind of reaction is this going to be? And I've got 2 elements here, and that's the only information that I'm given. I'm not given any info about the product, because that's what I have to come up with. If you go through the hints and the patterns that I've given you on types of reactions, you can see what this one really looks most like is a formation reaction. And in fact, it's a special type of formation. It's the type of formation you're going to be required to predict products from, called simple formation. And in a simple formation reaction, we are just taking a look at elements coming together to make a compound. So element plus element making compound. And that's what we have here. We've got magnesium and sulfur, 2 elements. Well, they're going to make a compound. What kind of compound will they make? What you need to recognize is that magnesium is a metal, sulfur is a nonmetal. The type of compound made by a metal plus a nonmetal is always an ionic compound. So, after you've decided, okay, this is a simple formation reaction, okay, I've got a metal plus a nonmetal, okay, it's going to be an ionic compound, well, what's now the formula and the name for this compound? Magnesium being the cation, sulfur, when it's an anion, remember, changes its name to sulfide. So the name of the product will be magnesium sulfide, whether you spell sulfide with a PH or an F. Okay? And now you just have to remember, how do I write formulas for ionic compounds, which is what magnesium sulfide is? Well, magnesium is a cation with a 2+ charge. Sulfide will form an anion with a 2- charge. And so when we cross those charges down, we get a formula for this ionic compound of MgS. Now, let's pay close attention here. The subscripts on Mg and S are not the same as the subscripts that we have written on the reactant side. That's very important that you know that. Subscripts in ionic compounds come from crossing the charges down. They don't come from anywhere else. So obviously, because the formula for this compound is MgS, we can see on the reactant side of the equation we've got 8 sulfurs. We need to do some balancing, right? So Because we need 8 sulfurs, I'm going to put an 8 in front of the magnesium sulfide and then an 8 in front of the magnesium, and that balances everything there. The last thing that you'll need to do is you'll need to assign states. So remember, magnesium and sulfur are found on the periodic table. So if I look there, I can see, oh yeah, these guys are both solids. So there we go. Magnesium sulfide, guys, if there's no water present in a reaction, you're going to end up with a solid ionic compound, okay? Never an aqueous, always solid unless there's water involved in the reaction. Then you'd need to use your solubility table, okay? For simple formation reactions, what you're going to be required to do is take a look at 2 elements, generally a metal plus a nonmetal, coming together to form an ionic compound, okay? That's what you're going to need to be able to do for formation reactions. When we look at the opposite of that, a decomposition reaction, okay, first of all, how do I know just from a reactant written that this is going to be a decomposition reaction? Well, decomposition reactions are really characterized by having just one reactant, which I can see right here. Okay, and so what you're going to need to do is predict products for simple decomposition. Now, what makes it simple? Is it necessarily easy? Well, no, that's not the simple part. The simple part is we're going to take a look at a compound breaking down into its elements. Now, I'll write element plus element here, but if a compound was made of 3 different elements, then it would be breaking down into all 3 of them, okay? Here we have water. It's going to break down into its constituent elements, so the elements it's made of, which are hydrogen and oxygen. What's the key here? The key is to remember that these guys are diatomic. Okay, so you can't just write H plus O. Hydrogen gas is found as H2, oxygen is found as O2. Speaking of which, some states on here. As I just said, those are 2 gases. Remember, water is going to be a liquid unless it's the product of combustion. Okay? And then we'll take a look at balancing here. If I have 2 waters and 2 hydrogen gases, that balances. If you're a little confused about the balancing, you can go back and watch that lesson where I take my time, build a table, and go through things here. So that is simple formation and simple decomposition. Now, the next type of reaction we're going to take a look at is a single replacement reaction. How did I know that this was single replacement? Because I can see that I have an element and a compound. And in fact, I've got an element and I have an ionic compound. That is generally even more characteristic of single replacement reactions, element plus ionic compound. So what happens here? Well, let's take a look. What I have is aluminum as my element. So I always check the element first, personally. Aluminum is my element. Okay, I know that aluminum's a metal. When it forms ions, it's going to form a cation, which is one that has a positive charge. Cool. When I look at this compound, iron 3 oxide, I can see my cation in that compound is going to be the iron. So what's going to happen is, because cations have like charges, again, they're never going to pair up. Remember, because like charges repel. So what's going to happen is the iron and aluminum not going to pair up. Instead, they're going to swap spots. Okay? So the aluminum ends up being paired with the oxygen, and the iron ends up being left on its own. Okay? How does this work? Well, I like to start with the element, okay? So the iron, which is going to be left on its own, I know is going to be iron from the periodic table, okay? It's nothing fancy. It's not going to be, there are no charges. There's no subscripts. Remember, subscripts only apply to diatomics, or that sulfur and phosphorus. Charges only apply to ions, which is not what iron is. Once it gets kicked out of its ionic compound right here, then it becomes an element. Okay? No charges. Iron. Period. The next thing that I have to do is I have to write the formula for that compound, now made of aluminum and oxygen. So again, I need to know about the charges. Aluminum forms ions with a 3+ charge. Oxygen forms ions with a 2- charge. When I cross those charges down, I will get Al2O3. That's aluminum oxide. Hopefully with the products and reactants up there, you guys can see how iron and aluminum have just swapped spots. Okay? Take a look at balancing here. If I balance, let's see, I'm going to need 2 irons and I'm going to need 2 aluminums, and that will balance. And then assigning states is the last thing. So I know for aluminum and iron, I can just look their states up on the periodic table. They are both solids, okay? And then, guys, metal oxides. Metal oxides, this is not one that you'll find on the periodic table. So write this note to yourself. Metal oxides are always solids, okay? What's a metal oxide? Okay, here's your metal, here's your oxygen. So it's an ionic compound made of a metal and oxygen. Always solid. Let's do another example of single replacement. If you would like to pause the video, go ahead and work through this next example on your own. Cool, go ahead and do that. In fact, the one after it, let me flip to that slide. This one here, potassium chloride and fluorine, that is a single replacement reaction as well. So if you want to go through and work on those, come back and check in with me. That's awesome. This particular example, we've seen this, right? This is my favorite single replacement reaction, copper plus silver nitrate. We've seen this reaction in play. Now, what's going to happen? Well, when we identify when we look at our element, we can see, okay, copper is a metal, means it's going to form cations. Okay, so it's going to swap spots with the cation in this ionic compound, silver nitrate. So it's going to swap spots with silver. So I know that silver is getting kicked out of the compound and it's going to be an element on its own. Maybe you've seen that, okay? If you've taken a piece of copper, added silver nitrate to it, you can see the crystals of silver start to appear. That's silver, solid, being formed on its own. Now what happens is the copper goes with the nitrate. The copper, when I started out with it, doesn't have a charge. Copper, as an element, does not have a charge. Only ions have charges, okay? So when copper goes with nitrate, I need to say to myself, okay, let's double check that periodic table. Right, copper is a multivalent metal. Copper can form ions with 1+ or a 2+ charge. How do I know? Am I going to get copper 1 nitrate or copper 2 nitrate? When I have the choice, this is a tip, so write this down. When I have the choice of which charge to choose, I always pick the most common ion charge. So if you look, the most common ion charge for copper is copper 2. So what's going to happen is I'm going to get copper 2 nitrate, and that is the formula for that. So obviously now this is going to need a little bit of balancing here. 2 silver nitrates and then 2 silvers. And it's also going to need states. Again, taking a look at the elements, those are probably the easiest ones to give states to because I can just look on the periodic table. Okay, and those are both solids. And then using the solubility chart for silver nitrate and copper nitrate, or perhaps you already just remember that all nitrate compounds are highly soluble, so those will both be aqueous solutions. The take-home from this particular example is when you have a choice of what charge to give something, a multivalent metal, then you always go with the most common ion charge. Our final example for single replacement reactions is, I put this one in here because I want you to know that there are reactions that involve anions swapping spots. So remember, as I said, always start by looking at the element on its own, fluorine. Fluorine, when it forms ions, it gains electrons, an electron to form fluoride. So I'm taking a look at the anion here, okay? And I am going to see in this compound that the anion is chloride. So these two, they're not going to get together. Again, like charges repel, they are going to swap spots. So what's going to happen? Chlorine's going to come out on its own. Now, what's something special I need to remember about chlorine? Chlorine's a diatomic. So when chlorine's on its own, it needs to be Cl2. Then potassium and fluoride are going to get together. Potassium with a 1 positive charge, fluoride with a 1 minus charge. So the symbol for that will be Kf. Okay. Balancing here, looks like we're going to need 2 potassium fluorides and 2 potassium chlorides. Finally, assigning states, again, these elements, if I take a look on the periodic table, both chlorine and fluorine are gases. And then looking at the ionic compounds here, you can use your solubility table. That will be aqueous. And I know fluoride is not necessarily on your solubility table. It's not on most solubility tables, but we'll go with aqueous for that one as well. If you've understood the concept of ions with like charges swapping spots, like we talked about in a single replacement reaction, then you'll be A-OK for double replacement reactions because it's the same thing happening. Look at this example. We've got sodium carbonate and cobalt 2 nitrate. I always pick one thing as a frame of reference, and what I'm going to pick here is the cations. I'm going to always focus in double replacement reactions on my cations. Okay, and those are going to be the two that swap spots. Some of you might want to think about anions swapping spots, which is 100% true. That absolutely does happen. I want to caution people against thinking both things swap spots. Otherwise, it gets a little bit confusing in the end, and you may come up with products that are the same as your reactants. So I always choose cations are the two that are swapping spots. Swapping partners, if you will, like swapping dance partners, like in a square dance. Okay? My 2 cations, sodium and cobalt 2. In this particular example, I am told which cobalt I'm using. Cobalt is a multivalent metal. Okay? In this example, I am told that I'm using cobalt 2. So the 2 compounds that I'm going to get when I swap, okay, sodium's going to come over here and go with nitrate. So I'm going to get sodium nitrate and cobalt's going to come over here and go with carbonate. And remember, that's cobalt 2, so it's a cobalt with a 2 plus charge. Carbonate has a 2 minus charge. And that's what we're going to end up with, cobalt 2 carbonate. If we go ahead and balance this, probably just by putting a 2 there, that looks great. And then assigning states, okay, if you recall, any compounds that contain a group 1 element have high solubility. Or if you don't recall, you can look that up on your on your solubility table. Go ahead and use that. Also, any compounds containing nitrate have high solubility. Oh, here's a compound that contains both nitrate and a group 1 element. That's high solubility. And then if we look up carbonate and on the solubility table, and we can see that when it is with cobalt, it has a low solubility. Okay, so that will be a solid forming there. So, One of the things that you will need to know about, or well, maybe you don't necessarily need to know about it, but one of the things that can help you out with predicting products for double replacement is that generally in a double replacement reaction, you are going to form either a solid precipitate or a liquid, okay, which remember liquid is different from aqueous. So we can take a look actually at our next example where that exact same thing happens. So here we have H2SO4 plus LiOH, so sulfuric acid plus lithium hydroxide. Okay, what are my cations? Well, in theory, H is my cation, H plus here. Lithium is my cation. They'll swap spots with one another. So that means lithium is going to go with sulfate. So I'm going to get lithium sulfate. Remembering that sulfate has a 2- charge. Lithium has a 1+ charge. And I'm going to get hydrogen coming with my OH. So I will get HOH, which perhaps you might recognize as H2O. Okay. This is an acid-base neutralization reaction, which is one type of double replacement reaction. Okay, and one of the products of a neutralization reaction is always water. That is going to be what our liquid is here. Figuring out the states of everything else involved in this reaction. Okay, H2SO4, as I said, that's sulfuric acid. All acids are aqueous. LiOH, using my my solubility table, I can see that lithium hydroxide is aqueous, and of course, so too is lithium sulfate. And if you are really excited and want to balance this, excellent. Let's put a 2 in front of lithium hydroxide and a 2 in front of the water. And I am totally okay if you want to express your water as HOH and you don't change it to H2O, as long as you know what that is and as long as we get the right state in there. Okay? So those are double replacement reactions. Again, with double replacement reactions, when we're taking a look at neutralization, remember that the H here is going to come and be with the OH here to form water. That's one tip on double replacement. The other tip that happened in this particular reaction here, the sodium carbonate and the cobalt-2 nitrate, is with the multivalent metals, I don't get to choose what ion charge a multivalent metal is going to be because that's already given to me. So the ion charge won't change from product side to reactant side when that particular metal is an ion on both sides. Our last type of reaction that we're going to go through an example for is hydrocarbon combustion. Now, we've talked about combustion reactions. Combustion reaction is anything plus oxygen. So that's what we're looking for as a reactant here. Anytime we see, oh, here's oxygen as a reactant, that's going to be a combustion reaction. And for you guys, one of the things that you will need to be able to predict, one of the types of reactions that you will need to be able to predict is hydrocarbon combustion. So that's a specific type of combustion where you have a compound called a hydrocarbon. Again, it contains just hydrogen and carbon, and that's being burned, which means it's in the presence of oxygen. Guys, these ones, maybe tougher to balance, fairly easy to predict the products. The products are always going to be the same. The products are always, for hydrocarbon combustion, carbon dioxide and water. And what you need to know is that both will be gases. So this is the one time where water is going to be water vapor as a product. Okay? Why does that happen? Probably because of the temperature that the combustion reaction is happening at. Think about if you burn a candle or if you light up your barbecue. Okay, both candle wax and propane in your barbecue are examples of hydrocarbons. Well, when you run a barbecue, you know, if you close the lid to let the barbecue heat up and then you open the lid to put on, you know, your chicken or your veg kebabs or whatever it is you're barbecuing, be sure to invite me over. You don't have a massive amount of water there, liquid water, that would be counterproductive. That would actually put out the flame. What you do have is water vapor. So water is a gas. That's a product of hydrocarbon combustion. So is the carbon dioxide. Carbon dioxide's always a gas for when we're predicting reactions here. Oxygen, I got that was a gas from the periodic table. Okay, and then methane. This is something that methane you need to know. Other hydrocarbons you might be given the states for, but methane is a gas. Going through and balancing this one. Okay, it looks like I need 2 waters, and then I'm going to have 2 oxygens here. Again, the first time through, I don't know if this is going to all sink in. Remember, we went through 5 different types of reactions in 8 examples. So what I really, really suggest is that you guys get in as many reps as possible. When you come up to an equation that you need to predict the products for, first thing you need to do is ask yourself, what type of reaction am I working with? And then you can go and move forward based on the knowledge of kind of the pattern that reaction follows. Keep in mind, again, 5 reactions that you'll be required to predict products for: simple formation, simple decomposition, single replacement, double replacement, including neutralization, and hydrocarbon combustion. Good luck. Let's get going on some practice questions, and we'll see how things go. Thanks, guys.